Okay. Please, Ilya, continue your...
All right. So, okay. So let me, I just wanted to illustrate the use of the replicas by deriving this famous Harris criterion that tells you whether disorder is relevant or irrelevant at a clean critical point. So let me imagine that I coarse grain my magnetic system. And it means that I essentially think about the various fields as being sort of smooth functions, maybe not smooth, but sort of defined in the continuum. And then the bond operator, SI becomes what I call the energy variable, right? It's a local energy variable. Okay, and we know that it couples to the thermal scaling variable, like a temperature, and the dimension of the operator E is XE, is related to the RG eigenvalue of the thermal variable. They add up to D, right? That's the usual scaling relation between the dimension of the operator and the scaling and the relevant RG eigenvalue. All right. So then the correlation length exponent in this case is going to be 1 over YT. That's another usual scaling relation. Okay, and so if you combine this, then you get the dimension of the operator of the energy operator is D minus 1 over nu. Now what I want to do, I want to now look at my Hamiltonian, and when I coarse grain it, and it's a function of the random bonds, I only keep random bonds for now. So random fields are separate. So, and in the continuum, I switch the notation, I call it the action instead of the Hamiltonian. It's the same thing really. It is the Hamiltonian, but it's just traditionally called the action. The field random bonds become some random, variable multiplying the energy variable here. All right. So that's my continuous action, and S star is the fixed point action, and then I want to replicate this, right? So that will be now the sum over A of the replicated things, right? What's important in the replica formalism is that you couple all the replicas to the same disorder realization, right? That's necessary. So the summation here is only over the energy is summed over, but J in front of it is the same for all the replicas. And then when I compute this partition function, Z sub n, so that's going to be some integral over all the replicas, realizations of all the spins in all the replicas. But what's also important is that I average this exponential over the disorder, and I will still write this as a product of the replica integrals, but of some effective action. This effective action does not depend on disorder anymore, and you can easily do this averaging simply assuming that you can introduce the cumulants of this disorder, right? And then the effective action will simply be written as the sum over the, of the SA fixed point actions. Then there'll be the first cumulant, which is just a number, kappa 1. This is the first cumulant. Then will be the second cumulant. And the second cumulant is, I'll write the formulas for this. But let me just first write DDR prime, kappa 2, R minus R prime. And here the double sum of the replicas, EA of R, EB of R prime, right? Plus dot, 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 of course. Okay, right? So let's see. So the cumulants here are simply kappa 1 is just the expectation value of JR at a given point, any point, and kappa 2 is the expectation value of JR prime minus kappa 1 squared. It's a connected correlator, right? Okay, so let's look at this structure back here. Well, as I said, the bond variables are typically uncorrelated. So if I want this to be sort of mimic this in the continuum, what I should say is that this kappa 2 is really a delta function. So it should be short range. It doesn't really matter how it falls away from for large distances. The easiest thing to deal with is just the delta function. So if I replace this by a delta function, then the arguments of these two variables collide, right? And we need to think about the OP of these energies with each other, okay? And so what happens is that the OP is very simple, actually. So if these are the same, you get the identity. If then you get something that is proportional to the energy itself. It's also proportional delta AB. But then if they're different, if A and B are not the same, then there's a new operator that appears, and this is just, let me call it EA-EB at the same point. Yeah, the way I think about it is very simple. So if you have this Ising model on a lattice and you bring together two bonds, let's say, then you can decimate the spin here, right? And that way you can reproduce this OP. If you sort of get rid of the spin, you trace it out, you'll get this OP.
Sorry, Ilya, maybe you want to answer to a chat question?
Yes.
Which is about. I can read to you if you want.
Yeah, go ahead, please.
It seems that by Yao, it seems that for the correlation functions you showed before, you average over ensembles before averaging over the disorder. But here you are averaging over the disorder first for the partition function. Does the sequence matter here?
So okay, let me first make a formal statement that so the formalism itself, right, is telling you that if you know the partition function for any value of n, and you can take the n to zero limit, you can reproduce all those correlation functions. Well, it was, I think I have these formulas right here. So these are the relevant formulas. And this type. So you see, these are disorder averaged of thermodynamic averages, and they're recovered from the partition function Zn. So maybe there's a question of whether these limits, like, I don't know, thermodynamic limit and the replica limit commute or not. That's a subtle question. There may be examples when it doesn't commute, but I'm not sure this is what is being asked.
Maybe just because here n is integer and you can, maybe because you are using the replica trick. I mean, I don't know.
Sorry,
no, so the whole, yeah.
Just because I'm also, I mean, now I think that I agree with the question. I thought that in order to take this two-point function that you have in this slide, you should not yet take the average over disorder, but first put the operators down, or say taking derivatives with respect to the coupling and then average. If you want to compute this literally, at Zn is not a function of the couplings anymore. So alternatively, you should know the partition function with sources, the Zn with sources. Is this correct?
Well, okay. So again, so sorry, Marco, maybe you can clarify what you're asking. Let me just attempt at an answer. So what is written here, right, is a correlation function in a system which has already been averaged over the disorder. Okay, so the Zn here is something that knows about disorder averages, right?
Okay, so I mean, let me try to rephrase. If I just know a partition function and I'm not allowed, I don't know.
No. Of course, yeah. To be able to bring down the observables, you have to introduce the sources. Certainly, yes. But then you can introducing the sources is not a problem for the replica method. You can certainly still average the partition function in the presence of sources and then take the derivatives. It's not a big deal.
Right. So I think if I interpret correctly the question, this was, I mean, either you introduce sources, but I think what the person asking was thinking of is you could also not average. Then you have the sources because you have all the couplings, all the magnetic field, etc. Then you take derivatives and then you average.
Right.
So I think this was the. Yeah. Thanks.
Yep. All right. So where we are. Yes. So what I wanted to do, I wanted to now just look at the what happens with these couplings that I introduce after the disorder average is taken here in this effective action. So the first cumulant simply adds to the term in the fixed point action, which has already this uniform coupling, right, to the energy. So the thermal variable. So it simply shifts the critical temperature, right? So this is innocuous in the sense that it just shifts the position of the fixed point. And the same happens with the OPE term that is proportional to the energy, right? The interesting term that is left is this term that is the perturbation in the effective action that looks like, so if I now take kappa 2 to be 2 gamma delta of r minus r prime, the effective action perturbation that I want to consider is gamma ddr, and then this sum where a is not equal to b, ea of r, eb of r. All right, so that's a term where essentially to now just, you know, I just have to find really the engineering dimension of this operator to decide whether it's relevant or not. And so it's easily done by just looking at the correlation function of this, or 2-point function of this operator at 2 different points. Sorry, not equal to b, not equal to d, ec of r prime, ed of r prime. And this is very easily computed because the replicas are independent. So this is computed at the fixed point theory, where the replicas are decoupled, right? And so this is really just an exercise in combinatorics. You really need to find how many contractions you can form of that type, right? Where 2 terms get contracted and simply give you, so they need to have the same index. So you simply need to count how many terms will have the same index for the energy operators at different points, right? So the whole thing becomes, if you count it, it becomes 2n times n minus 1 times the expectation value of the energy operator, sorry, correlation function of the energy operator with the same replica index squared, okay? And so this is proportional to the 1 over the distance with the 4xe here, right? So it means that the dimension of this energy operator, of the energy perturbation, this sort of the operator that perturbs the clean fixed point, is twice the dimension of the energy operator, okay? And then the corresponding RG eigenvalue, y gamma, is d minus 2xe. So if you count everything, it's 2 over nu minus d. And you can immediately infer that if y gamma is less than 0, or d nu is bigger than 2, the disorder is irrelevant. right? So that's the famous Harris criterion. Well, I want to make a couple of comments here. So first of all, Harris himself, when he derived this criterion, was using much more hand-waving arguments based on the estimates of the root mean square fluctuations of the local transition temperature within a correlation volume of the clean system. So imagine that you have a clean system, the correlation length is large, and then the disorder locally sort of shifts this temperature up and down. And then you want to see whether the fluctuations of the disorder of this temperature are bigger than the distance to the nominal transition temperature in a clean system, or smaller than that, right? That defines whether this disorder is relevant or irrelevant. So, and the estimation of the fluctuations that Harris was doing were using the central limit theorem. So in some sense, there was an implicit assumption that the distribution of the disorder is well behaved, and it has, well, in particular, all moments, and the cumulants are smaller, high cumulants are smaller. So in the field theory language, if I sort of try to rephrase this, then I have to sort of think about what happens if I include higher cumulants, right? And if the high cumulants are nice in the sense that they exist and maybe even decay with the number of the index of the cumulant, then the corresponding operators either produce the same things that have already been considered upon the OP, upon the when you do the OP, or they produce something that is less relevant. Okay, so they don't seem to change this criterion. But one has to be careful, because if the cumulants are not existent or very large, right, as what happens for broad distributions, the central limit theorem doesn't apply anymore, and all bets are off. So I think it's an open question of what happens if you have a very strong disorder in these cases. And sometimes, sometimes we do know the answer, sometimes we don't. But I think the status of the Harris criterion, it only applies to the systems where the disorder is well behaved in that sense, right? Second comment is that can be easily, sorry.
Yes, indeed, that's true. I mean, for example, polymers in a random environment, they are supposed to be affected by disorder, and they don't satisfy the Harris criterion.
But what does it have to do with the width of the distribution function of the disorder?
Yeah, it's because the renormalization group flow, if you set up the phase diagram for say the ON model, there's a critical disordered line that flows out of n equals to 1 and goes towards smaller values of n, but then it will turn around before it hits 0. Mm-hmm. Meaning that when you are at n equals to 0, so in the polymer limit, then you're not going to go to a finite disorder fixed point. You're going to flow all the way out to infinity.
Mm-hmm. Right. Okay. Well, I mean, but again, the way you phrase it, it's not clear to me that you're following the distribution function. So when you say infinitely strong disorder, is it just a one parameter flow or the whole distribution function?
Maybe that's a too complicated question to settle right.
Yeah, okay.
So why is this such a big deal? I mean, it's clear whatever fixed point you're considering, whether it's disorder or not disorder, you study stability around the fixed point, but it says nothing about some other fixed point which may exist somewhere very far away from the fixed point that you studied. I don't see why is it so special to disordered physics. It can always happen in any physical theory if you introduce some new variables. It can happen for the Ising model in principle as well. There could be, I mean, we think it doesn't happen, but it could happen that there is some fixed point which has Z2 invariance far away from the Ising model. And there are some systems which are described by that fixed point with some very different critical exponents. We don't know if it's true or not. There's no proof.
Yeah, so I mean,
Ising model.
Yeah.
There was a time at which we thought that indeed the flow goes away and doesn't reach a fixed point. But then we realized that there is a fixed point. However, it is of order square root of epsilon instead of epsilon. So it's very far away in a sense because it's square root of epsilon, which is larger than epsilon. But there is a random fixed point for that.
That's for the 4 minus epsilon, right?
Yes, 4 minus epsilon.
Yeah, so let me mention this. So I actually was going to say that. But okay, let me just say a few words about the Harris criterion, and then I'll talk about the fate of the fixed point. So first of all, it can be generalized to all kinds of other things. So it can be generalized to correlated disorder, where the cumulant decays as a power law. That's been done by Weinrib and Halperin. It can be generalized to quantum critical points, and in fact to all kinds of spatio-temporal disorder, where the correlations in space and time have, for example, different scaling. That's all possible. Secondly, it's very easy to generalize the same argument to random fields, okay? And it turns out the random fields are always relevant, and that's something that distinguishes them from random bonds and makes them somewhat different in spirit. So the more interesting question then becomes what happens to the ordered phases when you add disorder, random fields, and they can destroy ordered phases. But let me stick now with the bond disorder and consider the case when the Harris criterion is violated. So what happens to the disordered to the clean fixed point? So when the disorder is relevant, so d nu is less than 2, then you certainly have just, in addition to the usual thermal variable, you have another random direction. So both ut and u gamma, yt and y gamma are positive now, and we certainly have what's called the crossover phenomenon. We have the two relevant directions, and eventually, if you approach this fixed point, you will still flow away in some other direction. But where do you flow? It's not clear. So in fact, as Amnon mentioned, for a long time, people believe that disorder simply just rounds off the transition. It stops being a singularity. But now we believe that actually the singularity survives, except that it now belongs to a different universality class. So to say anything about this universality class, we can try to use various perturbative techniques. So for example, for the Ising model in 3D, and this is where I can quote the results of the conformal bootstrap. The energy variable has the dimension, what is it? 1, 4, 1, 2, 6, 2, 5. I don't know, maybe there's more digits by now. And d times nu turn out to be 3 over 3 minus xe. This is about 1.8899, certainly less than 2. So that's an example of the point where the disorder is relevant, but it is violated. The Harris criterion is violated only rather weakly, right? The 2 minus d nu is 0.11, so it's smaller than 1, right? Moreover, in d equals to 2, we know that d nu is equal to 2. And in d equals to 4, d nu is also equal to 2. Okay, so there are two cases where you have the Harris criterion is strictly marginal, right? And so you can imagine that you can do either a 2 plus epsilon or 4 minus epsilon expansions around those clean fixed points and study the fate of the disorder. And this is quite successful. And this is where I'm happy to say that maybe not so much conformal bootstrap community, but field theory community has been paying attention. There's a paper by Zohar, Komargotsky, and Simmons-Duffin that studied these limits recently. And of course, there's some specific results, what I want to mention is that what generically is known is that there's a theorem due to Chase, Fisher, and Spencer that that tells us that whatever happens, if you reach a critical fixed point when you flow along this relevant direction, so at the disordered fixed point, the new random new correlation length exponent should certainly satisfy the Harris inequality. Well, maybe up to a marginal case. So that's a theorem, right? So it sort of tells you that there cannot be a cascade of such crossovers. Once you get a disorder that is relevant, you simply flow to a different fixed point where this Harris criterion is now not violated. All right. Okay. All right. So now let me maybe describe what happens in the case of the marginal disorder. Questions? So, as I said, when this is exactly equal to 2, so that's a question, what happens then? And a priori, the Harris criterion doesn't tell you anything. You would have to go to sort of, some higher loop calculation to see what happens. And there are various scenarios possible. The disorder may still be marginally relevant, or it can be marginally irrelevant. So the clean Ising in 2D provides a very interesting case where you can study this rather well. So it turns out that if you do perturbation theory for this model, you realize that the disorder is marginally irrelevant, and it causes some universal logarithmic flow to the clean fixed point. So ultimately the fate of this is that the fixed point goes back to the clean fixed point, but on the way you get logarithmic corrections to scaling from the irrelevant operators, marginally irrelevant operators. This scenario, strangely enough, I mean, it's a perturbative calculation, so nobody was sure whether it's truly, strictly speaking, true or not. And I think up to quite recently, there was still some doubts about it and there's some controversy. But some recently very high accuracy Monte Carlo simulations actually provided support for this scenario. So that seems to be, I don't know, at least there's some consensus that this is correct. Well, why do I mention the Ising model as well? It's a special feature. So it's special in the following sense. The clean fixed point of the Ising model in 2D is described by Majorana fermions. So that's a very simple non-instructing theory, and we can certainly do a lot of. So that's one of the ways to study this system, to perturb these Majorana fermions by disorder and see what happens. And it turns out that, okay, I mean, from the replica point of view, you can certainly have to multiply your Majorana fermions. And if you do it in a way that is somewhat natural in this case, you consider the even number of replicas, then you can pair up these Majoranas into Diracs. 2 Majoranas go into a Dirac fermion. And then within the Dirac theory, you can easily study all kinds of perturbations. And so just conceptually, what happened when we did this fermionization is that immediately we go from the spin model to some kind of a random fermion model, right? And this is a class of models that I'll be considering tomorrow. And those are the models that exhibit Anderson transitions. So in a sense, there's a mapping between a spin system and a disordered fermion problem here. And this particular disordered fermion problem turns out to, by symmetries, only to allow disorder in the mass of the Dirac fermion. So this random mass disorder in the Dirac fermion is exactly this marginally irrelevant perturbation that leading to logarithmic corrections to scaling. And for the aficionados, and then again, something that I will discuss tomorrow, this is what's called the class D in the Untitled Chapter classification of disordered fermionic systems. All right, this fermionization of the Ising model can actually be done also for the strong disorder case. So one interesting case and I mentioned this because it leads to some interesting types of fixed points. So
maybe, can I ask a question just before?
Yes, go ahead.
What in the discussion of Harris criterion so far, did the replica index n play any special role? Because it looks like the theory you could flow to, like for instance, in this Lagrangian, would be very different depending on what is n.
Yeah, so that's okay. So that's a very good point. Thanks, Marco, for asking. So I was going to discuss this. So, well, maybe, sorry, what did I do? Did I erase anything? Yes. Okay. I actually, maybe not, well, let me say it here now. So look at this action here. So the point is that when you carefully look at the sign of the coupling constant in front of this perturbation, it's negative to compared to the usual perturbations that we consider in the system. So it's not, so it's a wrong sign of the coupling. So, and it might be naturally leading to all kinds of instabilities if you want, right? But what turns out is that the number of terms in this sum, if you count it, the number of terms is n times n minus 1, right? And so this number, even after you divide by n, if you want to do the replica limit, so what happens as very often in this business is that when n goes to 0, there's a very clear distinction between n bigger than 1 and n less than 1. And many things change sign when n goes to 0 limit. And that saves the day in the end. So what I'm trying to say is that you should really think about these theories as maybe not well defined for positive large n's, but then when n goes to 0, everything becomes okay. So you don't, well, maybe this is too vague. And replica method is not actually the best way to treat them. If you have an alternative such as supersymmetry, it's always better to do supersymmetry, then you don't have these issues. I don't know if this is answering your question or not, but
yeah, thank you.
You could get the same just by perturbation theory expanding in the disorder. So you don't need replica to show the scaling of this double energy term.
Yes, so I mean,
in the J's.
Yes, if you have
function,
right, if you have a weak disorder, right? If you have weak disorder,
for weak disorder, you get the same answer.
Right. Okay. Great. Thank you. Right. But so I wanted to mention what happens for strong disorder. So let me look at a specific model, this Ising model, and I can do it in any number of dimensions to begin with, where the distribution function for the bond disorder is the bimodal distribution of the full length type. With some probability, the bond is taking a positive value corresponding to a ferromagnet, but with another probability, it takes the value, a negative value, which is characteristic of antiferromagnetic interaction. So models with these distributions, bimodal distributions, are exactly the models that exhibit this variety of phases. So generic phase diagram for this model would look like this. So by symmetry, P can be restricted to the range of 0 to 1/2. And there's a clean transition TC that is suppressed by the disorder. And eventually, transition temperature goes to 0. And so this is the ferromagnet. This is paramagnet. And there's a spin glass in higher dimensions that looks like this somehow. So for sufficiently large values of P and sufficiently low temperatures, you have spin glass phases in these models. And notice that there's a multi-critical fixed point where the three phases meet, right? And that's a very interesting fixed point. This bimodal distribution actually belongs to a class of distributions, a Gaussian with, arbitrary variance and mean can also be used. In this class of distributions, the Ising model in any number of dimensions possesses a certain gauge symmetry along a certain line in this diagram. This line is called Nishimori line. That was discovered by Nishimori, and it goes exactly through this fixed point. Moreover, it is known that it's actually a renormalization group trajectory. So there's the directions of these perturbations are known in this phase diagram, and having this gauge symmetry allows you to say a lot of exact results about these features of the phase diagram. For example, one interesting thing is that the statement that this phase boundary is strictly vertical for this particular low temperature phase boundary. So what I wanted to say here is that in 2 dimensions specifically, you can do this fermionization procedure, and then the problem becomes that of some kind of class D random fermion problem. In 2D, the spin glass is believed to be absent for finite temperatures and only exists at 0 temperature. So this is 2D. So spin glass is here at 0 temperature, but the Nishimori point survives, and the Nishimori line survives, and everything survives. And so you can ask what happens at this fixed point. And so using supersymmetry, there was a paper that I wrote some time ago where we argued that this fixed point can be described by some supersymmetric spin chain. And this spin chain then can be mapped to a sigma model. And this is very similar to localization transitions, except that supersymmetry is somewhat different in this fixed point. Well, I'm trying to say that, again, this is one of the cases where there's a well-defined field theory, some supersymmetric sigma model, where we can hope to maybe apply conformal bootstrap eventually to study this. All right.
So maybe you should recall that there are also some very interesting identities on correlation functions.
Yeah, that's right. That's right. So along this
something like odd powers.
Yeah. So the story is different.
Powers.
Yeah. So what? Okay. So thanks, Jesper. So what Jesper is saying is that you can do the following. You can take any spin correlation function, you can raise it to an odd power, 2q minus 1. Q is an integer here, right? An average over the disorder. And along this Nishimori line, it turns out to be equal to the same correlation function raised to power 2q. So these powers turn out to be equal pairwise as you raise the q. So that's a very strange feature of this model, and it's not appropriate to the fixed point. It's actually along the whole line. Yeah. Any other questions?
Yeah, I had a question. Does J set a scale in this phase diagram? Is T measured in units of J?
Yeah. So T is 1 over J. Yeah, certainly. As I said, I mean, I just I switch between the varying J and varying temperature. It's the same up to inverse.
And what are the, I mean, like if you want to approach it as in a conformal bootstrap approach, like where is this point? I mean, like, do you know?
Well,
yeah.
Well, this is a big question. So this is what I was hoping to learn from this event. So how do you even start thinking about applying conformal bootstrap to some fixed point that you know very little about? I don't know. I mean, well, maybe somebody can suggest something. I mean, certainly, as I said, I hope that some internal symmetry may be a hint, giving you a hint. So whenever you have a supersymmetric sigma model, there's certainly all the fields are classified according to the supersymmetry. Maybe that's maybe that's something that will help you. I don't know.
For instance, the effective central charge, you can compute it?
For this particular fixed point?
Yes.
I think it's still C equals 0.
That if you divide it by n.
Oh, yeah, that I don't know. That I don't know. All right. So
suppose it as a possible target. This is our first.
No. As I said, I mean, I'm trying to be casting a very broad net. I mean, I'm pulling together all kinds of random fixed points, just telling you about them, and then some of them may be good targets for the conformal bootstrap. Some of them may not be. I don't know. But essentially, this rounds up the discussion of the classical spin models that I wanted to present. This is very, as you see, this very superficial and shallow. But again, we can go deeply into things. But there are many more things to be talked about. So let me look at the quantum models next. All right, so what is the quantum spin model? So these are models of the same type, more or less, as the ones I wrote classically, except that now I want to allow for my spins to be generators of some Lie algebra. And that's why I put a hat on them. Sorry, I'll be right back. Just give me a second.
Okay, we are on live. Okay, this is. Okay, nice. Okay, Omar, can you put on Slack so we can we are not losing your reference?
Maybe now that there is a hole, I could say that numerical people, they have actually computed these the exponents corresponding to these different powers of correlation functions, say for spin-spin, and they have also computed the effective central charge, and all of those are non-trivial numbers, and people don't understand what they are.
I'm sorry, in which model? Which model are you talking about?
I'm talking about this Nishimori point in this random bond Ising model.
So, okay, so in the random bond Ising model, there is a special, there is a normal, like weak disorder fixed point, which is more better understood, and there is Nishimori point, which is not so well understood. Is this the claim?
And yes, and for that Nishimori point, there are numerical measurements. So if ever you found a good way to bootstrap this point n, at least you could compare to some numerical results about these correlation functions satisfying this strange equality.
So but actually, I remember
diagram with Nishimori point. Where is the usual bond? Because we are in this Nishimori point exists in any D, as far as I understood. Right?
Yes, it does exist in any D. That's correct.
But for example, in 3D there is also the usual weak disorder fixed point.
So the weak disorder here is okay. So the flows that I showed here actually are exhibited for 2 dimensions. So this is this irrelevant flow into the clean fixed point, right? Yeah. For 3 dimensions, the whole thing may look different. So I'm not sure what, so yeah.
But presumably this Nishimori fixed point should flow to the usual, to the weak disorder fixed point in 3D.
So actually in 2 dimensions, you could also consider not the Ising model, but the 3-state Potts model with this kind of disorder. And then you would find that on this ferromagnetic-paramagnetic line that goes from the pure model down to n, somewhere in between, there would be another fixed point. And that fixed point would be in the same universality class as this weak disorder fixed point without the change of sign of coupling constant. Okay, so then you would get both fixed points in the same on the same figure.
So I guess what Jesper, what you're saying is that you're talking about this scenario here, right?
Yes, exactly. Exactly.
Mm-hmm. Yeah. Right. So this will be the weak disorder fixed point, and this will be a Nishimori point.
And so that would be my guess of what would happen in 3 dimensions then.
Yeah.
Or exactly for the Ising model.
Mm-hmm.
Okay.
Yeah. So what I wanted to say about the Nishimori point, there's another thing to be said here. It is for this point specifically that people looked at the multifractal spectra very carefully. So this point has this property of multifractal scaling for the moments of the magnetization, and that's the couple of papers by Choker. It's so exhibiting some very interesting properties. So I'll maybe mention it again when I talk about the Anderson transitions. Okay, sorry, let me try to quickly discuss the quantum spins. So, okay, so the basic feature of the quantum models is that these S hats are now generators of non-commuting generators of Lie algebra. So, meaning that the different terms in the Hamiltonian may not commute with each other. And so that's the typical setting for the quantum phase transitions. Quantum phase transitions when the competition is not between the energy and the entropy, but you can look at the 0 temperature ground state of the system and just vary the ratios of the coupling constants in the system, and you can have you can exhibit the transitions in different situations. All right. I hope this is clear, right? So one thing about the quantum problems is that the time now plays a special role. And it is something where Malte is probably a big expert. So it certainly may be exhibiting different scaling. The scaling in time may not be the same as scaling in space. So this possible anisotropy is encoded in the so-called dynamical critical exponent, Z, little z. Okay, I want to distinguish it from partition functions. So little z, which is defined as the following. So generically, you have a gap in the spectrum of your Hamiltonian, but when you approach a quantum phase transition, a continuum phase quantum phase transition, it disappears, and it turns that this scaling of the gap is related to the scaling of the correlation lengths in the system, and that's where the z exponent comes in, right? So when z is not equal to 1, the time and space are not on the same footing, right? Let me say it this way. The space-time is anisotropic. And so in this case, the conformal bootstrap is probably not possible in the sense that the whole system is not Lorentz invariant or not conformally invariant for sure, right? Because of this anisotropy. But there are many systems where z is equal to 1. Let me exhibit this in one particular case. And this case is the following. So it's a generic Hamiltonian that will be useful. So this is a Hamiltonian of the so-called transverse field Ising model, where you have the, I specifically use the sigmas for the Pauli matrices, and the hats are just a reminder of the fact that these guys with different indices do not commute. And I will, you see, I will just introduce the ratio. This G now denotes the ratio between the bond disorder, bond strength, and the field strength. So, but the field is not in the z direction, it's in the x direction, right? So that's what makes the system quantum, because the transverse field does not commute with the interaction of spins in the nearest sites. It's easy to sort of hand-wavingly establish the behavior, the phase diagram for this model. For G much larger than 1, we have order, and all the spins are more or less pointing the up or down direction, right? And if you turn on the transverse field, it does not commute with the SZ, but it flips the SZ. So it introduces the excitations on the top of the ordered ground state. And you can study these excitations, how they proliferate, how they propagate. Certainly for G less than 1, much less than 1, we have a disordered state where all the spins are along the x direction, but this is not diagonal in the original basis of the sigma of the z axis, right? So that's, so for some G critical, there's a fixed point that describes the transition between the two phases. And it turns out that this fixed point is in the Ising classical, Ising universality class in capital D equals D plus 1. So you start with the quantum system in little d dimensions, and you end up with the fixed point that is described by the classical field theory, well, classical Ising model in the one higher dimension. So this correspondence between classical and quantum is very, very useful to build intuition, and it's very central to the sort of understanding of this phenomena. So let me briefly give you a flavor of how you do this. So what you should be doing, you should consider the quantum partition function of the Ising model at a finite temperature. And let me restore the temperature units here for this purpose. And what you can do, you can trotterize this, right? Meaning that you write this as a product of multiple matrix elements summed over the intermediate states of this exponentials, but now taken with some small delta tau steps in the imaginary time direction, right? And these matrix elements are taken in the Hilbert space of the system, which is the, at each site, you have just a two-dimensional space, right? For the spinner that is sitting there. But then this whole thing is tensor to the power n, where n is the number of sites. So that's the big space where these states belong to, right? And so you have a huge matrix that, you know, eventually, if you multiply all these matrices, you get the partition function. Now, it turns out that these big matrices can be written in terms of the Pauli matrices that act locally in this space, okay? So this is a tensor space, this is a tensor product, right? It's a big tensor product. So you have sites that, you know, n sites, and each site you have just a two-dimensional vector space. So the whole matrix can be written in terms of the Pauli matrices acting locally on these sites. And it's amazing that the resulting transfer matrices are identical with the transfer matrix of the classical Ising model in D+1 dimensions, right? That's how the connection is established. One way to do it. By the way, the same kind of connection in 2 dimensions, so 1 + 1 dimensions, can be also directly inferred from the fermionization, because that fermionization that I mentioned can be done by for the quantum 1-dimensional model can be done using Jordan-Wigner transformation. And for the 2-dimensional transfer matrix, for the 2-dimensional classical Ising model, the transfer matrices can also be fermionized using the same Jordan-Wigner transformation. And they, again, exhibit the same identical structure. And it's another way of connecting to the fermionic problems, because once you apply the Jordan-Wigner transformation to the 1-dimensional transverse field Ising model, you get some free fermionic problem, just tight binding model for fermions in 1 dimension. Okay, quantum fermions in 1 dimension. Probably the last thing I want to say today is that once you imagine, so these quantum models exhibit quantum phase transitions, and so there's the same kind of issues appear when you add disorder. So once you start adding this disorder, you can ask the same type of questions, whether disorder is relevant or irrelevant, whether it leads to new phases, new transitions, and so on. And the only thing that I wanted to mention, that since we did the Harris criterion, the Harris criterion is for quantum system is still the same. It still involves D, which is the true space dimension. It's not D plus Z times nu bigger than 2. Because the disorder, sorry, I wanted to erase this nu, which is not very newish. When you think about the 1-dimensional, classical analog of the quantum system, the disorder is not really uncorrelated as we were thinking about it. It's certainly correlated along the time direction. In fact, it's perfectly correlated in time direction. Because it's frozen disorder, it does not fluctuate in time. And so in the corresponding classical system, the disorder is columnar, so to speak. It's correlated along the spatial direction. So if you think about this as sort of a lattice model in space and imaginary time, so different bonds are correlated in time direction. They're really the same, right? That's what I mean by columnar disorder. And that's what is responsible for the Harris criterion still being this. Okay, that's exactly 11:30. So I should probably stop here. Well.
Okay, thanks. So, question time.
A columnar doesn't look good for the bootstrap. I'm sorry to point out. Because probably Z is probably not going to renormalize.
Yes, so that's definitely not good for bootstrap. I agree. So what I want to, so what will happen in the future, actually, so when I start discussing Anderson transitions, I need these analogies between classical and quantum systems or going up in dimension, because I wanted to have some connection between spin chains, clean spin chains, and field theories for them. So the sigma models, which I'm going to discuss next time. And that is something that superficially is only relevant for clean systems, but in fact, many field theories for disordered free fermion systems map to some certain spin chains and certain sigma models, which are, so that connection is very similar there as well. So I just wanted to mention that. So I agree that interesting random fixed points in quantum systems are probably not easily accessible using conformal bootstrap because of this columnar type of disorder.
Maybe if I remember well, there is an exact solution of this model by McCoy. There was an old.
You mean, well, in one dimension, you mean?
I think that okay, McCoy did. I mean, he did. I think that he solved exactly the Ising model with columnar disorder, and then it was realized that it can be applied for the quantum case, and it is an example of a strong disorder point, right?
This is something else I wanted to discuss, but don't have time yet. I mean, I'm not sure even maybe I can say a few words right now, and if there's interest, I can say more tomorrow. But so this is a famous case. This particular Hamiltonian, especially in one dimension, which can be analyzed very efficiently for strong disorder when both the J distribution and H distribution are broad, right? That's a very fascinating. There's a very fascinating technique called strong disorder renormalization group that works directly in real space and essentially eliminates the strongest bonds in a recursive fashion. Okay, so if you, for example, if you have a strong bond somewhere, you integrate out the excited states of the strong bond, which couples the spins into either a singlet or a triplet, depends on what kind of the sign of this disorder. And so you can proceed with this procedure recursively, and you can develop the flow of the distribution functions of these bonds and fields. And that's been introduced by Dasgupta and Ma and developed to high sophistication level by Daniel Fisher. And it's called under the name of the strong renormalization group. And the infinite, so the fixed point that you reach in the end, ultimately, is very strange. It's called the infinite disorder fixed point, and it exhibits fascinating properties, such as some critical exponents turn out to be irrational numbers, like the golden mean and stuff like that. It's a fascinating topic, absolutely. And it's not clear, though, how to, I mean, there's some partial results in higher dimensions. So the point is that this decimation procedure, or this real space RG, is only useful for one dimension because it preserves the structure. In higher dimensions, that scrambles the lattice immediately, and then it's not clear what to do. Right. So that's all I wanted to say about this.
Can I ask? I don't know. This is maybe a question for Slava, actually, who made the observation. So you were saying, if there is columnar disorder, you would expect Z to renormalize, so to break rotational invariance, because I guess because there's a direction in the system. But no, okay, because there is already a direction in this. I was thinking you need a spin one relevant operator to do that, but you're saying it's already broken rotational invariance, so it will just grow Z. Was this the observation?
Yeah, that's. I think there was recently on some paper by Ofer Aharoni and I forgot the name of his collaborator, where they studied something like that.
But I guess the question, because if we start with the system with z equal 1, and then we add this disorder, which is columnar, then the question is if this is if this induces a spin 1 relevant operator, right? Because we start from a situation which is invariant under rotations, and then we're trying to break them. But at least at the fixed point, normally it's hard to have relevant spinning operators. So why is it? Why is this column? I guess the question I'm asking is why is this columnar, this directionality of the disorder relevant deformation, and the system doesn't just flow to the system with disorder in?
Well, it induces a non-local, since also this columnar disorder is also a non-local perturbation of your theory. It induces a non-local. I think, I mean, it's a paper of Aharoni and Narovlansky. It's an RG paper. I think it was pretty well written, so you can try to take a look. I'll post it.
Thank you.
There is a question on the chat that maybe you want to answer by Antonio Antunes. In the continuum limit with z equal 1, is there a way to see this quantum classical relation as just a weak rotation?
Well, no, not quite. I mean, I'm talking really about the systems with different dimensionalities, right? So I forgot to mention that actually I'm mostly thinking about Euclidean setting, right? When I already made the rotation to the imaginary time, but even after that, the quantum system is in d dimensions plus 1 time, and the classical system is in d plus 1 dimension. So I don't know if it really makes a difference, but yeah, and so it's especially striking when z is not equal to 1. Then these are really different dimensions. But maybe in the d equals 1 case, it is true that it's really about the weak rotation. So those points with z equals 1 correspond to gapless systems with a spectrum of excitations has the linear structure. So the energy of the excitation is proportional to its momentum, right? So it's essentially a linear spectrum that makes this, well, so it's relativistically invariant in that sense, right? And that's, then the weak rotation makes it into just one more dimension. Yeah, I don't know if it helps.
Yeah, so I have one question slash comment. When I mean, like when you talk about this random fixed point, you say that you do not know. I mean, there is always the question if they are conformal, for example, if you can hope to use bootstrap approach. So the question is, what is for you the mechanism? What is the why you think that the conformal invariance is put under question, or if you, for some point, you can have some arguments to think that they are conformal. The observation is that in general, when you use the replica trick, I just mentioned that it is also interesting. Also, before taking the replica limit, you have these coupled models. In that case, you have a fixed point, and in that case, I think that you can say that the system is conformally invariant because the unitary is sure. So they are like interesting model to study itself, the coupled one.
Well, okay, let me try to say something that first of all, I don't really know, right? So there was a discussion of Cardiriva paper, but the subsequent discussion touched upon higher dimensions as well. And my understanding, and please correct me if I'm wrong, is that there's some proof due to Polchinski that scale invariance in higher dimensions implies conformal invariance, provided some input. You need some input. And as far as I understand, one of the input is the unitarity. Is that correct?
Yes.
No,
So
but the message that I was trying to make is that it was a red herring. That it's this unitarity assumption that everybody makes in high energy community is not because it's essential, but because people just want to write papers.
Okay, so what's the true statement then?
It's not known. The true statement is generically it should be true.
So roughly speaking, unless something happens, we expect a scale invariant field theory in higher dimensions to also be conformally invariant.
Yes.
Right? Okay, that's my hope as well. So I mean, so that's why I'm talking about all this stuff. But on the other hand, I can tell you the following I mean, maybe I'll have time tomorrow to do it in more detail. Okay, so let me just summarize it briefly. First of all, there's a special Anderson transition called the spin quantum Hall transition in 2 dimensions that has the following features. A certain model for this transition can be exactly mapped to 2-dimensional bond percolation. All right. And so this model then is expected to be conformally invariant at the fixed point, right? Because 2-dimensional bond percolation is most certainly conformally invariant. Okay. A second statement, quite generic, is due to Martin Zirnbauer, that if you have a set of observables in your field theory that satisfy the so-called abelian fusion, if they're labeled by Q, like I had OQ, and you fuse it with OQ prime, what happens is that these indices simply add. That's what's called abelian fusion, right? And if these are primary operators, then you can prove, essentially it's a theorem, that the dimensions of these operators are quadratic in Q. It's a parabola. It's a polynomial of second order in Q. Okay. And such observables are known in the theory of Anderson transitions in terms of wave functions. So if you take a critical wave function, it turns out to be a multifractal, and the moments of this wave function scale with different exponents, this xq, and sort of naively, it's very natural to expect that these objects are satisfying abelian fusion, because a wave function raised to power 2 multiplied by a wave function raised to power 4 is the wave function raised to power 6, right? So maybe it's too naive, but at least there's some expectation like that. It's supported by a different story. You can certainly find the field theory operators in the corresponding field theory in the sigma model that do have this property, that they do satisfy the abelian fusion, all right? And so if they are primary operators, this theorem would imply that these scaling dimensions will be parabolas. Okay, well, the parabolas are pointing in the wrong direction, but that's a separate story. They're pointing downwards. So for large Qs, these are negative dimensions again, as I mentioned. Well, however, there's a precise numerics. Again, once you're dealing with numerics, you have to be careful. But there's a very, very careful numerical study of this multifractal spectra for this system. And they show the deviations from parabolicity. So there's in some roundabout way, if you do believe these numerical studies, then you don't have parabolic spectrum. Therefore, some of the assumptions that went into the proof of the parabolicity are not valid. And it's hard to see what should be violated here. So I don't know even if it's possible that one sector of the theory, that the percolation, that gives you low moments of the conductances, let's say, is conformally invariant, but some other sector of the theory, which gives you the multifractal operators and exponents, is not conformally invariant. it seems to be hard to reconcile, but that's the status, which is very confusing. And I was hoping maybe somebody can shed light on this. I don't know.
Well, here's Martin Zirnbauer. I feel I should maybe jump in and make a comment.
Please do.
Since I've been referred to. Slava earlier complained that in the discussion of multifractality, the system size appeared. That is a relevant remark. So in the study of conformal invariance, it's not a good idea to look at, in particular, do numerics for observables that depend on the system size. You may be lucky and you may get away with it, but sometimes you're unlucky and you get hit by a contradiction. So rather than going into a long lecture now about this, I would advertise that the people doing numerics study observables that do not depend on the system size. And I have written several papers suggesting how to do that. So that's my comment on this. I don't think there's any contradiction. The numerics should be
Martin, I should point out
observables that actually obey the principles of conformal invariance.
Yeah, but nevertheless,
do not depend on the system size.
So, Martin, so in the notes that I posted on Slack, and I hope to, make them slightly more polished. So I argue that the system size dependence of an endpoint function can be traded for the dependence to the distance to the point contact that you want to advocate in an infinite system for an n+1 point function, where the n+1st point is your point contact. It's the same, literally. So I don't think the finite system size is a problem.
Well, I didn't get. So Martin, what do you want to say? So you suspect that if one doesn't look at this system size dependent observables, then there's still conformal invariance. You somehow suspect that conformal invariance is just broken by boundary conditions at large L.
Yes, roughly speaking.
Okay.
What I'm saying is there are better observables to compute. They exist. They are in the literature, but so the numerics that Ilya is referring to is not new. It's not of the last years. It's like 10 years ago, even longer.
No, Martin. I am referring to class C numerics from Evers, which was recent, just literally a few weeks, maybe a week ago, was posted in the archive. Yeah, it's class C, not class A.
I have not seen the archive post, but I talked to the student who did this work, and I was not convinced they did this in the right way. You see, in class C, you have the extra problem that what's predicted are properties at exactly zero energy.
Yes, correct.
But in numerics, the way they do it, they never find an eigenstate at exactly zero energy.
True.
Yeah, so because they work on a closed system, they don't do what I advocate, they do something else. They work on a closed system where you have a discrete spectrum, and in 100% of the cases, the eigenfunction that you find does not have eigenenergy zero.
Correct.
So then you have to make a complicated analysis to correct for that. I'm not convinced that these people did this properly together with the necessity to do all the rest of the finite size scaling, which by itself is already difficult enough. So no, I'm not convinced that this recent study by Evers and company proves there's a violation of conformal invariance. I believe that the class C is described by a conformal fit theory, and I believe we will soon know what it is.
All right. Well, your task is to explain 1/8, I suppose. But that's a different story.
Maybe we can also, this can be put on also on the like discussion, so we can follow. I mean, like that. So there are other questions. So if not, we can call it a day.
All right. Thank you.
So thanks, Ilya, for your very nice lectures. So that will continue tomorrow, right? Yes.
See you tomorrow. Yep.
Okay. So see you all tomorrow, and as usual, I will send the Zoom links in the morning or in the night. Okay. So thanks you a lot to everybody. A good evening.